Okay, there's one other thing I want to mention here that I forgot to about PuTTY, that if you're using this as your terminal software, it doesn't support, I believe by default, I haven't used it extensively as I have the other ones, but one of the things it doesn't support is tabs normally, and I don't believe by default it also supports the login scripts. But what you can do is there's an extension for it that is called the PuTTY Connection Manager, and this does support that. So if you install this as the add-on for PuTTY, then it looks a little bit more similar to how Secure CRT does, where it has the dialog that you can save the different devices. So then for the rest of the connections as you're doing them throughout class, you won't have to keep typing in the usernames and passwords. Now additionally, looks like the Windows machines are now loaded, where these should be listening at the host name is npvpn.ini.com. Your port number is going to be 60,000 plus your rack number. So if you're on rack 5, you're going to be 60,005. The login should be admin, and the password is Cisco CCNA, all lowercase. So if you open up your Windows remote desktop connection, then from here, this is Windows 7, so yours may look a little bit differently depending on what version you have. But if you go to the options here, it'll ask you some things like you can change the display size, you could change the local resources. One of the things you probably do want to do is under audio settings, turn this off, say don't play or don't record, and then don't share your clipboard, or no, you could share the clipboard, don't share printers with them, because otherwise it takes up a bunch of bandwidth for these machines that we don't need. So we don't need to hear the audio from the remote Windows machines. But here under General, when you connect, this is where you would put the name. So here I have npvpn.ini.com:60,001 because I'm on rack 1 here. Now when you connect to this, it should give you a normal Windows login, and then eventually you're going to get to the desktop that looks like this. So it's just a normal Windows machine. If you look at, and let me change this to make it a little bit more readable. Let's see. Okay, can you guys read that font okay now? So this is the Windows machines command line then. From here, if you were to look at the IP config, you could see that it has an address assigned. Right now it has the address 192.168.0.1. Its default gateway is set to 192.168.0.254. Now right now, we don't really care about the gateway because we're not going to be routing with this machine as of yet. But the key is that right now it's on the same subnet as what I configured at least one of the switches when I was doing the initial configuration dialog. Now assuming that the actual physical diagram is correct and that there's no problems with the connections, right now this inside NIC card on the machine is 192.168.0.1 with a mask of /24. And I was configuring the switches. I want to say that it was switch 2. That switch 2 had the IP address. I'm going to look at the show, show IP interface brief. Switch 2 has this address assigned, 192.168.0.7. Now, without any other configuration, it should mean now that this address should be able to reach the Windows machine that's in that same subnet. So if this connection is working from the switch, I should be able to ping 192.168.0.1, or from the other way around. So I would go to the Windows machine. If I ping 192.168.0.7, then likewise we could see that there is connectivity over the network. So essentially this means that the result of the logical topology, which was the result of my configuration, is that essentially this Windows PC looks like it's directly connected to switch 2. They're on the same IP subnet. The test PC is 192.168.0.1, and switch 1 has the address 192.168.0.7. Now, even though in the middle of the network here, there's essentially other devices, so this could be considered a network cloud, where I don't know the specifics of how the traffic actually got from the PC to the switch, but really at this point, we don't really care how it's getting there. Just the key is that since they're in the same VLAN now, and we're going to talk about that in more detail tomorrow, exactly what that means, but I can now test with some of these basic IP tools that if up to our layer 3 and beyond connectivity is working. So based on the fact that I was able to go to the switch and ping this address, which ping uses a layer 3 protocol that is ICMP. It's the Internet Control Messaging Protocol. Basically, what I'm doing is just asking the machine, are you alive? And then it's replying back with an ICMP echo reply. So the ping on the way there is called an ICMP echo. I'm just asking the machine, are you running IP? It's replying back with the echo reply saying, yes, I'm running IP, my host is alive. So this is telling me a couple things then about what's going on in the communication between them. If we look at this within the scope of the OSI model that we talked about before, ICMP is working at the network layer. It's a layer 3 protocol that runs on top of the rest of the layer 2 and the layer 1 network. So this protocol with the pings is a good test just to make sure that the physical connectivity between the devices, so we would say that this is our Windows machine, and then this is really switch 2 here. But I now know that there's nothing wrong in the physical layer between them. So somehow there's physical connectivity. Somehow there's also Ethernet connectivity, which is running at layer 2. And I now know I have connectivity up to at least layer 3. Now this tool, ping, is probably one of the most basic network testing tools there is out there. It's just going to tell us that there's nothing wrong with the physical network underneath. It's also going to tell us that if the devices are not on the same subnet, that the IP routing feature is working between them. So we'll talk about that in more detail when we get to routing. But if the Windows machine and switch 2 were not on the same subnet, but they were still able to ping each other, it means routing is fine. Now right now they are on the same subnet, so they don't need to route to reach each other. They're just going to have local connectivity in what's known as the broadcast domain, is where people who are sharing the same subnet are going to be. Now this doesn't necessarily tell me that their applications are working or that they have the correct presentation layer for things like ASCII encoding. But if I were to have something wrong with one of my network applications, let's say like I can't reach my web server, one of the first things I may want to do is check, can I ping the server from my client? Now if I get a response back in and it says it's successful, this now eliminates some problems from the potential troubleshooting of the network. it tells me that I'm guaranteed that, well, not 100% guaranteed, probably 90+% guaranteed that there's nothing wrong at the physical layer. Because if layer 1 was not working, it means that everything else above it is going to be broken. If layer 2 is working, or excuse me, if layer 2 is not working. If layer 2 is not working, then likewise everything above it is going to be broken. But based on the fact that at layer 3, this is where ping is working, and I was able to ping from the source to the destination, what does this tell me about the communication between them? If in order for layer 3 to work, layer 2 and 1 have to work, and layer 3 is working, then what does it tell me? Okay, at least basic layer 1 and layer 2 networking is fine. It doesn't necessarily mean that there's nothing wrong with like the TCP transport between them, or that there's nothing wrong configuration-wise with the actual application, like your web server is set up wrong. But at least now I know that layers 1, 2, and 3, those are working. So when you're trying to troubleshoot problems in the network, some of these basic tools are going to eliminate where the problem definitely cannot be. Another one that is useful is going to be the Traceroute feature. Now, Traceroute right now, we can't see in detail exactly why this is going to be helpful, because the devices are on the same subnet, they're on the same VLAN. But from the switch, if I were to say to traceroute to 192.168.0.1, what this is going to tell me is who are all the networking devices that are running IP in the path from me to them. So it's going to show me on a hop-by-hop basis, or basically on a router-by-router basis, who are all the devices in between and what are their addresses. Now, the delay on the switch, the reason why this is happening is that by default it's trying to do a DNS resolution for this address, but I don't have a DNS server set up, so it's delaying it a little bit. But if I were to do the same thing from the Windows machine, in this case their command is traceRT to 192.168.0.1. It says that, or not .1, .7. And I believe the Windows machine is trying to do the same thing also. It's trying to do DNS resolution. What we should see, it says it's only one hop away. What this means is that these devices are on the same subnet. And from a logical perspective of the networking diagram, they're the same as being what we say is directly connected. So even though there may be other physical devices in the network between these two, like other physical layer 1 switches or layer 2 switches, from an IP point of view, it appears that they're in the same subnet, which means that they're in the same broadcast domain. Or from a routing point of view, what we say is, again, that they're directly connected. Now, for cases where there are multiple hops in the network, if the topology looked like, let's say we have the PC, and then this connects to router 1, and then from router 1 we go to router 2, from router 2 to 3, then from 3 to the switch. If I were to run the Traceroute application here, and if there's a problem on the link between router 2 and router 3, that's going to help me find that out, because if I can get to router 1, it means there's nothing wrong in the communication here. If I can get to router 2, it's going to tell me there's nothing wrong in the communication here. But if I can't get to router 3 next, it's possible that there could be something wrong with the communication between 2 and 3, or somehow from me to 3 or back. So essentially, by the process of elimination, we're going to be able to use these tools to figure out what's wrong in the network and then exactly what we need to do in order to fix it. So when we get into our layer 3 routing, we're going to come back to this. This is going to be really useful. But right now, since they're directly connected, it's not really going to help us that much. What I should also see is that since I configured the switch for the virtual terminal access, or what was the VTY access, when I look at the show running config, again, on the switch, the switch has this password set up under line VTY04. This was part of the initial config dialog. This means that the switch is now listening for telnet access from me. So on the Windows machine, if I were to telnet to 192.168.0.7, it's now going to ask me for that password that I configured as Cisco. And now essentially I have remote management access to the switch. Now from here, if we look at the show privilege, it's similar to the default console access I had, where right now I only have read-only access to the device. But assuming that I know what the enable password is or what the enable secret is, I should be able to get to privilege 15 and then now make changes remotely. Because remember, with our current design, even though from this room we're not physically connected to switch 1 or switch 2, from the network point of view it looks like we are, because we have this console port that's connected with this RS-232 serial link that goes to the access server. Then from the access server, it has a connection to the internet. But essentially from the switch's perspective, the management session is coming from here, where we're connected. This is why we were able to reload the router's configs, and then after they come back with a blank configuration, we were still able to access them, because it's coming from that out-of-band or OOB management interface. Now, if I were to do the same thing from telnet access, that's not going to be the same result. So from the switch, if I were to write erase and then to reload, since I'm connected through telnet, it immediately stops running the IP protocol when I start to reload, and now you lose connectivity to the device. So this type of management here, when you're coming in from telnet, this is considered in-band management. So in-band management protocols would be like telnet or SSH. The serial console that we went through the access server, that's considered out-of-band management. Okay, the next step we're going to do is to essentially put an IP address on all of the machines here, all of the routers. And then we're going to go through the process of looking at the version of software that we're running. And I'm going to standardize it so that they're all running the same version of code. Because right now I think they're running a mix of different versions. So in order to do this, I'm going to be running on the Windows machine what's known as a Trivial File Transfer Protocol, or TFTP server. A TFTP server is kind of like an FTP server, or kind of like a web server, where you could transfer files between it. The difference is that for TFTP, it's usually made for the management of network equipment, where TFTP runs over the UDP protocol. So if we were to think of this as from the OSI stack, the application is TFTP, but at layer 4, this runs over UDP. Then at layer 3, it's going over IP. At layer 2, we're running what protocol here? We're running Ethernet. Then at layer 1, this is Cat5 copper cables. So from the TFTP server and the TFTP client, this is going to be like the router. What essentially should happen is that when these two communicate, the application is going to start and say, I want to transfer a file from router 1 to the server, or vice versa. So from the server's perspective, the packets are going to go down the stack. They get encapsulated inside this UDP packet. So essentially we're going to have the iOS image. Then inside of that, we're going to be adding our UDP header. From layer 4, it goes down to layer 3. It adds the IP header. From layer 3, it goes down to layer 2. It's adding the Ethernet header and the Ethernet trailer. where this trailer here, this is the cyclical redundancy check, or the CRC. Basically, this is an error check that it's doing in Ethernet. But the packet gets down to Ethernet. Finally, it goes over the copper cable. It goes across. Then as it starts to go back up the stack, these individual layers get peeled off. So it gets to layer 2. Layer 2 is going to decapsulate, or basically remove, the Ethernet header. It gets to layer 3, it's going to remove the IP header. It gets to layer 4, it's going to remove the UDP header. Then eventually the application, which is TFTP, says inside this is the iOS file that I'm trying to transmit. So our first step in order to do this is then to get basic IP connectivity from the devices to the server. And if this is configured correctly, we can test that we can get to the server just by doing a basic ICMP ping. So if I can ping the server, it means that my layer 1 is working, the physical cables, the layer 2 Ethernet is fine, and then layer 3 IP is configured correctly. So previously we did this by doing the initial configuration dialog, but now I'm going to do this manually from the command line. So let's say we do it on router 4. So router 4 started up, it went through its power on self-test, or the bootstrap. So after I was reloading it, it eventually comes back. It's going to ask me, do I want to run the initial configuration dialog? I said no. And then it says press return to get started. So after you hit enter a bunch of times, then it's going to get down to this default prompt, which is just says the router's name. From here, I'm going to go to privilege mode by typing enable. And now we need to make changes to the router, so we need to go to what's known as global configuration mode. This is with the configure terminal command. Now we'll see as we start to make changes in the iOS, either on the routers or the switches, when we go to make a change, you'll see that the prompt name changes to inside of parentheses, there's a different type of mode that is listed here. This one here is considered global configuration mode, or simply global config. Global config is going to have the word config inside of parentheses there. If we were to want to make changes to the interface on router 4, let's say fast Ethernet 0/0, we would go to the config interface mode, or I would say config-if inside of parentheses. So the key is that based on looking at the prompt of the router, you can tell where you are in the hierarchy of its configuration. If you're making changes that affect everything, which is globally, or if you're making changes to a specific interface, or you're making changes to like an IP routing protocol. So from global configuration, the next thing I want to do is to go to my interface, this link here, fast Ethernet 0/0, and I want to put an IP address. I want to give router 4 the address 192.168.0.4 with a subnet mask of 255.255.255.0. So to do that, I now need to go to the interface configuration mode. We say INT for interface, and then the interface name. If we say question mark, it's going to show you every different possible type of interface, but this router doesn't actually have all of these configured. So let's say that we don't know what the name of the interface is. We're trying to figure out what's the naming convention that this particular router uses. We can see this by, let's exit out of privilege mode, or exit out of configuration mode, global config, and we'll say show IP interface brief. This is going to give me the names of the interfaces, like fast Ethernet 0/0, fast Ethernet 0/1. It's going to tell me, is there an address currently assigned? Right now there's nothing assigned. These ones we don't need to worry about for right now. The status, this tells you, is the link functional? is the link non-functional for a hardware reason, or is the link disabled because of a software reason? This administratively down means it is shut down in software. So if we were to look at the show running config, it's going to say under interface fast Ethernet 0/0, it's going to have the shutdown command. So let's say show running config. Under fast Ethernet 0/0, this has the shutdown command. Okay, so we need to get rid of this. This is one of the first things we need to change. That if the interface is administratively down or simply shut down, we can't use it for anything. So we need to bring it out of that state first. Once we do that, then we can assign an IP address and then test our basic connectivity. Now, some of the other options like the speed and the duplex, we'll talk about this more in layer 2 switching tomorrow. So I need to go to global config, configure terminal, or simply config T. So from config T mode, from global configuration, I'm going to go to interface, fast Ethernet 0/0. Now the numbering here is going to depend on the individual platform. Some of them are going to have more numbers between the slashes. It depends on if it has multiple slots in the router or multiple modules. But regardless, you can always see what the naming convention is when you look at either the show run is going to show it or the show IP interface brief. But from this output here, show IP interface brief, it doesn't tell me how the router is physically connected to the rest of the network. This is the reason that we always need this, the physical network diagram that says fast Ethernet 0/0 on router 4 is connected to fast Ethernet 0/4 on switch 2. Because I need to know what interface do I want to put the address on. If I were to put it on FA 0/1, then that's not going to work because that's not actually physically connected to anything here. So I'm in global configuration, then I went to the interface configuration mode. From here I'm going to put the IP address. 192.168.0.4. Then the subnet mask 255.255.255.0 and say no shutdown or simply no shut. Now if the interface is working, so if there's nothing wrong with like the physical cabling, I should get two separate log messages. One of them says that the link status changed up, which is an indication of the layer 1 status of the interface. Then it's going to tell me that the line protocol changed state to up. This is an indication of the layer 2 status, where layer 1 is going to be your physical cabling. So if the cable is unplugged, the link status is going to be down. If there's something wrong with the layer 2 protocol, like Ethernet or PPP or frame relay, the layer 1 status could be up, but the layer 2 status could be down. And we can see this, all of the different variations, when we look at, again, that show IP interface brief. If the interface is functional, I want to see that the status is up and that the protocol is up. Where again, status here, this is talking about layer 1. Protocol here, this is talking about layer 2. So it says no, there's nothing wrong with the cabling, there's nothing wrong with basic Ethernet. At this point, I should now be able to do my basic ping test, where if I can ping 192.168.0.1, I want to make sure that I have some level of success here. Okay, we'll talk about in more detail tomorrow and Wednesday why it lost one of those pings. But if I try this again, it should say it's 100% successful. If I want to send a bunch of these, you can add additional commands onto the ping command. Like, what's the repeat count? Let's say I want to send 1,000 packets. It's going to do the ping 1,000 times. This would show you if there's some sort of intermittent problem, like in your layer 1, where maybe you have some sort of like weird electrical interference on your cables, and sometimes it's causing a problem, sometimes it's not. If I were to send a ping and let it run for an hour, and then if I see that I have maybe 95% of packets are going through, that's probably an indication of a problem. Because under normal circumstances, you should have 100% of the packets go through between the directly connected devices. Okay, but success rate is 100%, so I know now at least what's working here between them. So here's the PC, here's router 4. If I can send the ping, which is the ICMP echo, and I get the ping reply back, which is the ICMP echo reply, then I know out of the OSI layers at least what is working. At least 1, 2, and 3 are working. So there's nothing wrong with IP, there's nothing wrong with Ethernet, there's nothing wrong with the physical cabling. Now I don't know if the PC is actually running the TFTP server yet, because I didn't check that high in the layers. But I now know at least up to this point, if I try to transfer a file and it fails, it's not IP's fault, or it's not Ethernet's fault. So as you'll see, a lot of, like the OSI stuff, it can get kind of boring when we're talking about that, but in the long run it does have a lot of application for networking, especially when you're trying to do this verification or troubleshooting. You'll see that as you get more experience with this, you eventually always think about at least typically these lower 4 layers when you're doing verifications. That you should be able to look at a network problem and almost immediately be able to figure out at what layer or below is the problem. So if I know that ping is working and there's still a problem, the problem is somewhere up here. But if the ping is not working, then I know it could be something below here. So it's a real good, quick troubleshooting tool. Okay, the next thing I'm going to do is let's do this on all the other routers real quick. Okay, let's go to router 1. And we'll do the same thing. We'll go to enable mode. We'll go to global configuration. We'll say config T. And also for clarity to show which devices we're working on, the other one thing I'm going to add here is a host name. Say host name is router 1 or R1. On router 2, host name is R2. On router 3, host name is R3. Router 4, router 5, switch 1, switch 2, switch 3. Okay, so now at least I can tell the devices apart just based on their host names. On router 1, if I look at the show IP interfaces brief, it shows similar output to what router 4 did, but the difference is that I don't have the same number of interfaces on this device. So there's a physical difference where this router has only one fast Ethernet interface, where router 4 had 2 of them. It has fast Ethernet 0/0 and fast Ethernet 0/1. Additionally, it has 2 serial interfaces, serial 0/0, serial 0/1, where router 1 only has 1 of these. This is a physical function of the router. It means that there's different modules or there's different WIC cards in one of them versus the other. So next, let's go to global config, and under the IP or under the fast Ethernet interface, I could either type the same thing, the whole thing. I could type interface fast Ethernet 0/0, or the shortcut would just be INTF 0/0. So as long as this is unique and I can hit the tab and it's going to complete it, then I know that it's going to be, I can issue that command. So if I were to say int tab f tab, you can see it automatically completes fully to interface fast Ethernet. So here my IP address I'll say is 192.168.0.1. Subnet mask is 255.255.255.0. Then I want to enable the interface, no shutdown. This command here, end, it's going to exit you all the way back to exec mode or back to privilege mode. Now again, we can see the couple log messages. It says the link up down message told me that interface fast Ethernet 0/0, the state changed to up. So this is telling me what here? Okay, there's nothing wrong with the cable, so layer 1 is fine. The line protocol message, up, down, said the line protocol on interface fast Ethernet 0/0 changed state to up. This means that what is fine? That layer 2 is fine. So there shouldn't be wrong with the basic cable, there shouldn't be wrong with the basic Ethernet config. So next let's try our ping. We ping 192.168. Let's try to ping router 4. Okay, we have connectivity to router 4. The Windows machine had what address here? Windows machine actually has the same address, 192.168.0.1. What we're probably going to see then is that router 1 is going to generate an error message that says we have a duplicate address on this segment. And I may not actually see this until we start to try to send traffic out. But the router is actually going to try to detect this problem automatically. Let's see on the Windows machine if I can get it to generate this. There we go, duplicate address. It says the IP process, and the way that you want to read these logs is that this is the timestamp. Okay, the timestamp by default was based on the uptime, which again is how long since the router reloaded. It says that there is from the IP process, so this means it's a layer 3 logging message. Duplicate address, this address was detected on fast Ethernet 0/0. It was sourced by this, which this series of numbers and letters means what here? This is a MAC address. So it's telling us that there's someone on the same Ethernet LAN as us that has the same IP address. And this is not a valid network configuration. So we'll talk about why tomorrow when we get into LANs in more detail. But you cannot be on the same VLAN as someone else that has the same address as you. So the logical layer 3 addressing or the IP addressing has to be unique, at least on the individual LAN. So I'm going to leave router 1 as what its current address is. I'm going to change the Windows machine instead. So on the Windows properties, and you can do this, if you're following along, you can do this either way. Okay, you'll just see on the Windows machine, you can set this to whatever you want. Just don't change the one that says do not change. Okay, if you change this, you'll lose access to the remote desktop. So this one on the inside, you can do whatever you want with that one. So on the inside adapter, I'll just move this to a new address. Let's say 192.168.0.100. So now from router 1, if I ping 192.168.0.100, okay, now it's successful, which again is telling me that there's nothing wrong with layer 1, 2, or 3 from router 1 up to that machine. The rest of these, I'm going to do this pretty quickly. So just on the fast Ethernet interface again, I would say no shutdown or no shut, and give it an address. So essentially, everyone is going to have an address that's in the same subnet, and they should all be able to reach that server. On the switches, this is going to be on their VLAN 1, which we'll talk about it in more detail tomorrow, why it has to be there. Switch 2 already has its address, and then switch 3. And that is 8. So if this is working, again, the list of addresses would be here. And then let's say the PC was 192.168.0.100. If everything is working, I should be able to go back to the Windows machine and now ping any of these addresses. Ping 192.168.0.1, 2, 3, 4, 5, 6, 6 works, 7, and switch 2 I actually reloaded without saving those changes. So switch 2, I need to put this back again. Show IP interface brief says VLAN 1 is unassigned, so it has no address and it's shut down. So I need to fix that. I'll say on VLAN 1, no shutdown, IP address 192.168.0.7. Now you'll see that by default, as you're making these changes, the router's console and the switch's console runs its logging process as what's called asynchronous, where basically it means that when I generate a log message, it interrupts it between my characters that I was typing, which can get kind of annoying at times. So you can see like I was typing the 7, I was typing the dot, and then the log message came up, and then my characters finished over there. So it's kind of hard to connect those two and read it. There's two things that you can do to fix this. If you're making a change, let's say on interface VLAN 1, I shut this down. This is going to generate a log message. So you can see it cut off my output at the end of the line and finished it down there. There's a bunch of character codes that the router takes on its command line process. If you do Control R, this is to refresh the line. So if you hold Control and hit R, it's going to return that. You don't necessarily have to learn these, but if you spend a lot of time in the iOS, it gets much easier to know what these control characters do. Like Control Z, this is the equivalent of the command end. So if I hit Control Z, it goes all the way back to exec mode. So I'll show later where these are located in the documentation. But there's a bunch of basically editing commands. Like Control D would be to delete your previous character. Control W is to delete the previous word. And I believe these come from VI for character editing. I may be wrong about that, but there's some Unix equivalent with these control characters come from. And then Control A is the beginning, jump to the beginning of the line. Control E is jump to the end. So there are other ones. These are pretty much the ones that I use. These four are definitely useful when you're editing long configs to jump around. But that Control R, this one can be useful when this happens. Okay, the other way that you could fix this is a property of the line console 0. Okay, line console 0, that's where we're connecting from the access server. So this is where the out-of-band management is happening. Under here, if I were to say logging synchronous, this fixes that problem with the log, where now every time that it comes up with a log, it automatically returns my previous characters. So if I say end here, it generated its log, but then it refreshed my line automatically. So a lot of times people put this under line con 0, is logging synchronous.
Is there a disadvantage to doing that?
Not really. Just if there's tons of log messages, between each one, it'll return the line over and over. Okay, so again, on the Windows machine, I should ideally have connectivity to everything now. Let's see, why can I not reach 192.168.0.7? Okay, let's look at the switch. I want to know, did I actually assign this address correctly? Let's look at the show IP interface brief. It says that the address is 192.168.0.7. So I put the address on there, but what didn't I do? I didn't say no shutdown. It's still in the administratively down state. So I need to go to that link and say no shut, and then it should enable it. Okay, now from the Windows machine, I should be able to ping the switch. Okay, so now I could reach all 8 of them. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, not 8, so I'm still missing one of them. No, there we go. Okay. Now, if I were to look at this from a logical topology point of view, we know that in the physical topology, the network is wired like this. But from a logical point of view, the network is going to look like this, where router 1, router 2, router 3, etc., all of these devices, they appear as if they're on the same local area network, on the same LAN. A lot of times in diagrams, when you have more than 3 devices on the same LAN, you'll see it drawn out this way, because this comes from originally in networking, these devices shared this same physical cable, where this was what was known as a 10 base 2 or a 10 base 5 cable, which was basically like a coax cable, like your TV cable, and then all the devices hang off of this, so they share the same physical connection between them. But in today's network diagrams, usually this is used to show a VLAN, that they're in the same VLAN, which means they're going to be in the same IP subnet. Okay, so the next thing we're going to look at is the management of the iOS images, or the software version. So I have basic IP connectivity between everyone. So all of these devices can ping each other. Next thing I'm going to do is look at what's the current version of software we're running. We can see this when we look at the show version output. You'll also see that show version is normally run during the normal boot up process. So up here somewhere towards the top, it should have already told me this info. So here, this is the output of show version. Now, there's a couple key things that I may want to know from this. Okay, one of them is, what is the current running version in RAM of the router? This says I'm running a version of iOS that is for the 2600 series routers. This is Advanced Enterprise Services K9-M. Now, from this, you can't really understand what this means unless you actually know the naming convention. It's not really important what this means. Okay, but what we're mainly concerned about is what is the main version, what is the subversion, and then what is the sub-release. So here it says the main version is 12, the subversion is 4, and then the release is 10. So this is the 10th release of the version 12.4. You'll see that a newer version of code than this would either say something like 12.4.10a or 12.4.11, where the numbers are eventually going to increment until they go up to the next revision, which is 12.4t. Then from there it goes to 15.0, 15.0t, and the naming convention just gets incredibly complicated with the way the iOS versions work. So if you want more information on this, you can look it on the website. If you search for like iOS train naming, Guide to Cisco iOS release naming, and it shows what this means. So there's all these subcodes that they use inside here to tell you exactly what it's for. Most of the time you don't need to do this. Okay, if you see a version that you don't know what it means, you can take the actual name of the file. So this is the single file that like you would download from Cisco's website. And what you can do is go to just the main Cisco website. If you go under support, and then let's say support, and downloads, this would be under routers. Actually, would be under, no, it's not going to be under this. Let's go to cisco.com/go/fn. Okay, it would be under that other site, but I would have to have a login that has a service contract, and I don't have that one with me right now. You can say search by image. This is called the feature navigator, which the URL for this is cisco.com/go/fn for feature navigator. Okay, this site is really useful if you're trying to figure out what version do I need to install if I want to run a specific feature, or if I'm trying to figure out what's the difference between two versions of software. And this is something that's not really very obvious. And when I was originally getting into Cisco networking, I probably went maybe a year or more before I finally figured out that there were actually different versions of iOS. And it only happened because I was trying to implement something, and I couldn't figure out why it wasn't taking the commands. That the documentation was showing this is the command you use in order to do it, but it turns out there's different sub-releases that this feature is on in this version, but is not enabled in the other one. So that's what it shows you, even inside of like this version that we have here. So even though this is the main release 12, sub-release 4, and then the maintenance release 10, of 12.4.10, there may realistically be 1,000 versions of 12.4.10 that are for different platforms and are for different feature sets. And the different feature sets have the different type of protocols that they support. But what you can do is take the file name, and under the feature navigator here, you say search by image. Search by image. And then you just paste the image name in. It's going to tell you exactly what it is. This is Advanced Enterprise Services for 2610XM or 2611XM, where the main release is 12.4.10. Then you'll see it could also be for 2620 or 2621 or 2650 or 2651. So some of the different hardware platforms can run the same software versions, but you would see that there's a version that runs on the 2600 that's separate from a version that runs on a 2800 or that runs on a 1700. So the main platform has its individual basically compile for that version. Is not going to work on the other ones. Okay, now let's go to the other routers and let's compare what they have. From these, let's look at the show version. And I'll do this quickly on everybody. Now the switches are definitely going to be a different version because they're a different hardware platform. But I want to know, are all of these routers running the same version? It says the system image file name is, it's on the router's flash, which is like a USB flash. It's just an internal storage for files. This is the file name, which it technically doesn't tell you what it is, because I could change this name if I wanted to. So it would be like renaming, any file in Windows to a different name. You could set it to whatever you want. This here tells you what is actually booted. So I could change this where it says Cisco ios.bin, and it's still going to work, but there's really no reason you would want to do that. Normally you just leave the default image name. So if we look at the other ones, I want to know, is anyone else running a different version? Okay, some of these are router 3, 4, and 5. They are running 12.4.25b, Advanced Enterprise Services. So they have a newer version of the iOS than router 1 and router 2 do. So I'm going to change router 1 and 2 to match the other ones. We're going to upgrade its version. Now there's a couple different ways that we can do this. One of them is to use the router itself as the server for the files. So if we look at the previous diagram that I had, as long as everybody has IP reachability to each other, or basically so everyone can ping each other, I should be able to go to router 3 and tell it to run the TFTP server process. So it's basically listening for someone to ask it for a file, which in this case the file I'm going to ask it for is its iOS image. So router 3 is going to be the server. Router 1 is going to be the TFTP client. And the configuration for this is really simple. All I need to do is go to router 3 and tell it what file in its flash I want it to offer to the other devices. So on router 3, if we look at a dir, just like in Windows directory listing, on my main flash file system, I have this image name, C2600-Advanced Enterprise Services K9-MZ.12425B.bin. In global config, I'm going to tell it that I want it to be a TFTP server. Specifically, the file I want it to serve is in flash, and this is the name. Okay, you can see when I hit the question mark, it already knew what files were in flash. That's the one that I wanted to serve. Now, from router 1 as the client, I need to tell it to ask router 3 for this file and then copy to its own local flash. We'll say copy the file. Where's the source of it? Okay, it could be coming from a web server, could be coming from an FTP server. In this case, it's coming from a TFTP server. So copy TFTP : just like a normal URL would be in a web browser. So TFTP : //192.168.0.3/ then the file name. And where do I want to copy this to? I want to copy this to my own flash. So I'm going to delete the file that I have in there and replace it with this one. So it asks me, do I want to save it as the same name? Okay, I could change the name here if I wanted to. There's no real reason to do it, so just hit enter. Now at this point, it's not actually getting the file, it's just checking, is that the correct name? So it asks router 3, are you running the TFTP service? It replies and says yes. Now it's going to ask me again, am I sure I want to do this because I have to erase my own flash to do it? And it asks me to confirm again. Because if I erase the flash and then I reboot, there's no iOS image. So it's going to go into like iOS recovery mode. So now it's eventually going to delete its own flash and then download that file from router 3. Okay, this is one option where you could use the router itself as the server. But in most real network designs, what you would want is some sort of dedicated server to run this process. So some server that keeps all of your iOS images, all of maybe your configurations, so that if you do need to do recovery, you have a single point that you can get everything from, which is what we're going to do here with this Windows machine. So on the desktop here, there's this application TFTP D32. This is the TFTP server. So I want it to be a TFTP server, and I'll say the directory, I'll just put these on the desktop for right now. Okay, you can make any changes to these machines you want. The VMware virtual machines, when we reset them, it deletes everything. So just change whatever you want, it's fine. And the interface here, I want to make sure that you have to choose the inside address. So here it's 192.168.0.100 because it has 2 NIC cards. Then I should be able to tell one of the other routers, like let's say router 4. I'm going to tell router 4 to copy its iOS image to the PC, so to upload it to them. We'll say copy it in the reverse direction. So copy from flash. This is my image name. And copy it to the server. So to TFTP : / 192.168.0.100. In this case, the server just automatically gets the file. This would depend on your server's configuration. I could set it here to ask for like a login and password, but by default it just automatically accepts the file. Now normally what you would want to do in a real network before saying that this feature is 100% complete is I would want to do a verification against the source file and the destination file to make sure that none of the data was actually changed in the transit. Because if even just one bit is different in the destination file, it's not going to work when I actually go to load it. Now the router is going to check that when it tries to boot it if the signature of the file is correct. But if it's wrong, bless you, if it's wrong, then the problem is the router's not going to boot its image. So typically once you do that, you would want to run like an MD5 hash or an SHA hash on the file. That's not really related directly to the routers. That's just a check to make sure that the source file and the destination file are the same. And I want to say that in newer iOS you can do this. Let's say MD5 iOS file verification. iOS image verification. This says this was added in 12.2.4t. So I should be able to do this here. That says verify /MD5 and then the name. Let's see if these platforms support this. And let's try this, let's say on like router 5. If we say dir flash, this is the file name, and verify /MD5. Okay, this version can do it. Verify in my flash, what's the signature of that? and eventually it's going to spit out a series of characters. I would then go to the Windows machine and get some sort of application on Windows that runs MD5, run it against the file, then compare the two values. If they're equal, then I know nothing has changed between them. So this isn't really directly related to the image transferring. Just this is kind of like a good best practice that you would want to do. Okay, so while it's actually downloading these files, let's take a short break here, and then we'll look at the result of what happens on router 1 once it is actually done downloading the file. That we should be able to compare the hash that 5 generates. It should be the same as 1's. And then if it is the same, then we can reload and it should boot the new version.